Hello friends, I hope you are doing great. IBM is here to bring you the last episode of electricity and DC circuits. I think this is part 8. Not forget, if this is your first time on this channel, you can go through the video description and you get every document that you may need to follow when you are using these videos. The documents are completely free, you can just download them. Check under the video description. Do not forget, after part 9, the next will be solving February March papers. And I think I'll solve paper 2, then I'll go to the formation of solids, and later on I'll solve paper 4. For those going to school, I think you will enjoy paper 2. So you will go to school when you have already gone through February March paper 2. I don't want to waste much time. I want to take you to the document and we go to part 8 of DC circuits and electricity. I think in part 9, in part 8, I think we stopped at page 180. And in part 9, I want us to start from page 181. Okay. So here we are. The unknown EMF E of a cell is to be determined using a potentiometer circuit. The balance length is to be measured when the galvanometer records a null reading. This is called the null method of taking a measurement. The measurement is correct when the galvanometer gives no reading. So what is the correct circuit to use? So first of all, we eliminate A. Why? Because here the positive terminal is going to be going to the negative terminal. We shall never get balance if the positive is joined to the negative. Similarly, in the same way here, the positive is joined to the negative. We can never get balance. Even the position of the galvanometer is wrong here. The galvanometer can never give a zero reading when it is connected in this point, in this position here. Then for B, I think B is correct because the positive terminal is joined to the positive terminal and the position of the galvanometer is correct. Then if we move the contact of the galvanometer here along this wire, there is a point where the resultant current through the galvanometer will be 0, then balance will be established. D is wrong because of the position of the galvanometer. It will never give a 0 reading. Reason, although here positive is joined to positive, normally the EMF here of this driver cell, if I call this one EMF of the driver cell, ED is always greater than E. So we can never get a balance point if the galvanometer is put in this position here. So our correct answer is going to be precisely B. What amount of charge flowing the given time will produce the largest current? Of course, current is equal to charge over time. Now we are going to do inspection. Because current is charge over time, we want the amount of charge that will give the largest current using the time for the time given there. Number 1, we have a charge of 4 coulombs divided by a time of 1 over 4. I think that is 16. So this is 16 coulombs. I mean 16 amperes. B is 4 divided by 1, which is 4 amperes. C is 1 over 4 amperes. And D is a quarter divided by 4, which is 1 over 16 amperes. So we see that the largest is going to be A. A 12-volt battery is charged for 20 minutes. By connecting it to a source of EMF, the battery supplies 7.2 times 10 power 4 joules of energy in this time. How much charge flows into the battery? So first of all, we know that energy is equal to power times time. So energy is equal to IV times T. And you and me know that charge is equal to I times T. So precisely we are saying that energy is going to be equal to charge times V. So we want charge. Charge is going to be the energy, which is 7.2 times 10 power 4 divided by PD, which is 12. So 7.2 exponent 4 divided by 12. This gives us 6,000 coulombs. So our answer is going to be D. What is meant by e.m.f? e.m.f, remember e.m.f is the energy converted from other forms to electrical per unit charge. The energy converted from other forms to electrical per unit charge. So energy is always converted into electrical. So we first eliminate this one is into electrical. This one is transferred by the driving cell, by the cell in driving a unit charge through the external resistance. This one is going to be PD actually. Energy transferred by the cell in driving unit charge through the cell, that is actually PD. The energy transferred by the cell in driving unit charge through the internal resistance, that is lost volts. The energy transferred in the EMF of the cell is the amount of energy needed to bring a unit positive charge from infinity. That is not EMF. So the answer is going to be A. The EMF of the cell is the energy converted into electrical when a unit charge passes through the cell. So that is EMF. EMF is actually energy per unit charge, but is energy transformed from other forms into electrical per unit charge. Two cells of EMF 3 volts and 1.2 volts and negligible internal resistance are connected to the resistors of resistance 9 ohms and 18 ohms as shown here. What is the value of the current I in the 9.0 ohm resistor? So I'll just put a loop here in the upper part of the circuit. I'll put a loop which is anti-clockwise. So sum of EMFs, Kirchhoff's second law, sum of EMFs will be 3 minus 1.2 because when I move anti-clockwise, the EMF, this one will be negative and this one will be positive. That's why I'm saying 3 minus 1.2 should be equal to the sum of PDs. There's only one potential drop here, which is 9 times I. So it means I is going to be equal to, that is 1.8 divided by 9, which I think is 0.2. 1.8 divided by 9. So that is 0.2. So our answer here is going to be B. 6 identical 12 ohm resistors are arranged in two groups, one with 3 in series and the other in 3 with 3 in parallel. What are the combined resistances of each of these two arrangements? So these ones are in series, we just add, they give us a total of 36 ohms. And these ones are in parallel, we get 1 over 12 plus 1 over 12 plus 1 over 12. This is 1 over total resistance in parallel. Remember I said if you have resistors in parallel, total resistance is always less than the resistance of 1. And this in parallel, their total resistance is going to be, since they are 3, it will be simply a third of the resistance of just 1. Let's try to see that. 1 over resistance in parallel will be equal to, this is 1, 2, 3, so that is 3 over 12. 3 times 1 over 12. Then we get the reciprocal, that will be 12 over 3, which gives us 4. 4 is a third of 12, so that is 4 ohms. So in series it is 36, in parallel it is 4 ohms, so the answer is D. The diagrams show a light-dependent resistor in a circuit P and a thermistor in circuit Q. How does the potential difference across the fixed resistor in each circuit change when both the brightness of the light-dependent resistor and the temperature of the thermistor are increased? Okay. If light intensity is increased here, light intensity is increased. It means the resistance here decreases, which means the PD here decreases. And if the PD here decreases, it means the PD here increases. So in circuit P, because they want how does the PD across the fixed resistor change. So in P, it increases. In P, it increases, so we ignore these ones which are saying decreases. Then for the thermistor, if temperature increases here, then the resistance of the thermistor is inversely proportional to temperature, so temperature resistance decreases. The PD here decreases, and if the PD here decreases, it means the PD here increases. So the answer is going to be D. In a circuit P, the PD in the fixed resistor increases. In circuit Q, the PD in the fixed resistor also increases. So our answer is going to be D. Which equation is used to define resistance? We have power is equal to current squared times resistance. Normally we define resistance as PD per unit current. So the answer is going to be C. Potential difference is equal to current times resistance, which means resistance is PD per unit current. The variation with the potential difference V of the current I in a semiconductor diode is shown below. What is the resistance of the diode for applied potential difference of positive 1 volts and negative 1 volts? So negative 1 is, I think, here. Negative 1 is showing that the current is 0. I think that means resistance is equal to infinity for negative 1 volt. Then positive 1 volt is here, which is showing that the current is 5 ohms, 5 milliamperes. So resistance is going to be V over I, which is going to be V is 1.0 and I is 50. It is actually 50. It is 50. 50 times 10 power negative 3, 50 milliamperes. So it means 1 divided by 50 exponent negative 3. That gives us 20. So the resistance there is 20 ohms. So let's check the alternatives. So we have seen for positive 1 it should be 20, for negative 1 it should be infinity, so the answer is going to be A. At a circuit junction, a current I divides into currents I1, I2 and I3. These currents are related by the equation I is equal to I1 plus I2 plus I3. Which law does the statement illustrate and on what principle is the law based? So this is Kirchhoff's first law. The sum of currents into the junction is equal to the sum of currents out of the junction. And this one is based on conservation of charge. That one we are now familiar. It's Kirchhoff's first law, not second law, and it is conservation of charge. So our answer is going to be A. The combined resistance RT of two resistors of resistances R1 and R2 connected in parallel is given by that formula. Which statement is used in the derivation of this formula? So if resistors are in parallel, the PD across them is the same. So let's see. The current through the resistors are equal, that is when they are in series. The potential difference across each resistor is the same, so the answer is B. When the resistors are in parallel, PD is the same. If they're in series, current is the same. In the potentiometer circuit below, the movable contact is placed at N on the bare wire XY such that the galvanometer shows zero deflection. The resistance of the variable resistor is now increased. So resistance here increases, resistance here increases. It means the PD across this point must be increasing. Therefore, the PD across the bare wire must decrease. So PD across XY must be decreased because the resistance here has increased, which means the PD here has increased. So the PD across the wire XY has decreased. Okay. What is the effect of this increase on the potential difference across the wire XY and on the position of the movable contact for the zero deflection? So the PD across XY has decreased. But remember the EMF here remains the same. The PD across XY has decreased. Therefore, and the EMF across EY, the EMF EY must remain the same. So first of all, we can eliminate some of these. The PD across XY has decreased, so we eliminate A and B. But then, note that the EMF remains constant. And remember the EMF, okay, EMF EY is the same, remains the same. And remember, we have seen that PD across VXY has decreased, which means the PD per centimeter, which is a constant. The PD per centimeter is going to be smaller because this is a constant, but it is depending on PD per centimeter depends on the PD across xy divided by the distance xy. So because this one has decreased but xy has not changed, so it means the PD per centimeter has decreased. And remember, the EMF EY is going to be the PD across xn times, which is the same as the PD per centimeter, which is a constant, PD per centimeter, then times the length xn. So because the EMF across y is constant, yet the PD per centimeter has decreased, EMF across EY is equal to the PD per centimeter times the length xn. Remember, this is constant, but PD per centimeter has decreased. If this decreases, to make EY to be constant, the length xn must increase. What does that mean? To increase the length xn, then the contact must be moved towards y. Therefore, our answer is going to be D. The PD across xy decreases. The position of the movable contact must get nearer to y so that the EMF remains the same. So the answer is going to be D. 6 resistors, each of resistance 5 ohms, are connected to a 2-volt cell of negligible internal resistance. What is the potential difference between terminals X and Y? So of course this is the negative potential. This is at 0 potential. To find PD across PD, you can find potential at Y, which is the PD across this one here, and potential at X, which is the PD across these two here. We use the potential divider formula. So I'll say potential of PD at X, potential at X is going to be equal to resistances there are 5 plus 5, which is 10, over total resistance in that branch, which is 15, times the voltage supply, which is 2. I'm using the potential divider formula, that is V out is equal to the resistance there over total resistance on that branch, then times V supplied. So this gives us 10 divided by 15 times 2, which is 1.3 or 4 over 3 volts. Then let's find the potential here. The potential at Y is going to be, the resistance there is just 5. Total resistance on that branch is 5 plus 5 plus 5, which is 15. Then times the voltage supply, which is 2. So you have 10 divided by 15, which is 2 over 3. Now we want potential difference. So difference in potential is going to be equal to 4 over 3 minus 2 over 3, which is giving us 2 over 3. So our answer is going to be A. Which electrical quantity would be the result of a calculation in which energy is divided by charge? This is either EMF or potential difference. So we have current, potential difference. The answer is potential difference because it is either EMF or potential difference. PD, energy transferred from electrical to other forms per unit charge, and EMF, energy transferred from chemical to electrical per unit charge. So it is either EMF or PD. A wire carries a current of 2 amperes for 1 hour. How many electrons pass a point in the wire in this time? So we know that charge is equal to the number of electrons times the charge of each electron, which is equal to current times time. So the number of electrons is going to be current times time divided by E, which will be current is 2 amperes, the time is 1 hour, which is 1 hour, which is 3,600 seconds, divided by the charge of each electron, which is 1.6 times 10 power negative 19. So we have 2 times 3,600. Sorry, 2 times 3,600 divided by 1.6 exponent negative 19. So that is 4.5 times 10 power 22, making the answer to be D. The diagram shows a circuit in which the battery has negligible internal resistance. What is the value of the current I? So to find the current I can just use Kirchhoff's second law. I can use Kirchhoff's second law. I'll put a loop here. I'll put a loop there. So when I put a loop there, I don't know the current here. So let me find total resistance then. Because I don't know the current in this part here, I'll just find total resistance. Total resistance R total is going to be, these two are in parallel. Because they're in parallel, the product over the sum will give us total resistance in parallel. So that is 6 times 3 over 6 plus 3, which gives us, that is 18 divided by 9, which gives us 2. So here the 2 in parallel give us a resistance of 2 ohms. Now 2 ohms is in series with that 2 ohms, giving us a total resistance of 4 ohms. So total current, which is the current going through 2 ohms, total current is going to be the e.m.f divided by total resistance, which is going to be the e.m.f is 12 divided by 4. So total current is going to be 3 amperes. It is the current which goes through 2 ohms. So the current coming here is 3 amperes, so it divides here. Note that 6 ohms is twice 3 ohms. If the current here is I, then the current here should be twice I. That is simple logic. If the current in 6 ohms is I, then the current in 3 ohms should be twice I, because 6 is 2 times 3. So, and current is inversely proportional to the resistance. So I can simply say that I plus 2I should give me 3 amperes, which means 3I is the same as 3 amperes. So I is equal to 1 ampere. So the current I is 1 ampere. Alternatively, I could find the PD across 2 ohms. The PD across these fixed 2 ohms. So PD across 2 ohms is going to be the current times the resistance. The current is 3. Current going through 2 ohms is 3 times the resistance, which is 2, giving us 6 volts. That is the PD here is 6. That means the PD across the parallel combination should be 12 minus 6. PD across the parallel combination should also be 12 minus 6, which is equal to 6 volts. So if I know the PD across here is 6, then the current I is going to be the PD, which is 6, divided by resistance, which is 6, giving us 1 ampere. So the answer is going to be A. The diagram shows currents I1, I2, I3, I4, and I5 in different branches of a circuit. Which one of the following is correct? So we see as if they are dealing with Kirchhoff's first law. So I1 is entering, I can say I1 is entering, I2 and I3 are leaving, so this is I2 plus I3. We have that equation, I1 equals to I2 plus I3, so this is correct. This one is wrong, this one is wrong, this one is wrong, because the other equation would be, at this junction, I3 is entering, so we can have I3 plus I4 is also entering, giving us I5, which is leaving. That is the other equation we can have, and I don't see it here. We don't have such equation here, so it is either this one or this one, which we don't have here, so we have only that one. The diagram shows two circuits. In these circuits, only the internal resistance differs. Internal resistances differ. Okay. So the answers to this table are the answers to that question are the ones at the bottom here. This is coming here. This was just a mistake. Which line in the table is correct? Okay. Potential difference across 3 ohms resistor, potential power dissipated in 3 ohm resistor. Is it greater in X than in Y? Let's check. We can find the PD here by just finding the current. Here the current is going to be the EMF 1.5 over total resistance, which is 3.5. And the current here I think is 1.5 divided by 3.5. I think that is 3 over 7. 3 over 7, that is the current there. And the current here is 1.5 divided by 3 plus 2, which is 5, which is I think 3 over 10. 1.5 divided by 5, that is 3 over 10. So you see that current in X is greater than current in Y. That's number one. The current in X is greater than the current in Y. But remember, current is equal to, remember V is equal to I times R. The resistance is the same, 3. Resistance is the same, but current in X is greater than current in Y. So it means the PD in X is greater than the PD in Y. So let's check that. PD across 3 ohm resistor is greater in X than in Y. So we eliminate these two. C and D are out. Then let's check the power dissipated in the 3 ohm resistor. Power is equal to I squared times R. Power in X, the current was 3 over 7, but this is squared, times the resistance, which is 3. The power in Y, the current was 3 over 10, this is squared, times the resistance, which is 3. So we can evaluate that since the current here, or we can check this mathematically. Open bracket, 3 divided by 7 squared times 3. Well, that is approximately 0.55 watts. Let's check here. 3 divided by 10 squared times 3. This is 0.27 watts. So the power in X is greater than power in Y. Power in X is greater than power in Y, so our answer is going to be B. The PD in X is greater than that in Y, and the power in X is greater than that in Y, so the answer is going to be B. Then we go back to this question. Which diagram shows a potential divider circuit that can vary the voltage across the lamp? A potential divider circuit that can vary the voltage across the lamp. This one will never vary the voltage across the lamp, because the potential at this point will always be the potential across the battery here, and the potential at this point will always be the potential across here. So the PD across the lamp is constant. This one here also, because there will be a short circuit, current will take this route rather than the variable resistor. So it means the PD across the lamp will always be constant, because this potential here is the same as this, which is the same as that. The potential below the bulb is going to be the same as that. So the PD across the lamp is always constant, so that will not vary. Then I think the answer is C, because as we move the contact to this point, the PD across the lamp changes, may go to 0. If we move to this one, the PD across the lamp may go to a certain maximum value. So the answer is C. This one is equivalent to this one, because even if you move the contact, the potential here is the same as the potential here. And the current will not take this route when there is a resistor here. So the potential here is the same as the potential here, which is the same as the potential here. Whether you move the contact to and fro, there will be no problem, there will be no effect. So it means this one is also not going to vary the PD across the lamp. So our answer there is going to be precisely C. Which of the following describes the electric potential difference between 2 points in a wire that carries a current? Electric potential difference. Okay. The force required to move. Electric PD is not the force. The ratio of energy dissipated per current. Energy over current, that is not PD. The ratio of power dissipated between the points to the current. power over current, I think that is V. We know that power can be equal to IV. So power can be, V can be power over current. So the answer is going to be C. The ratio of power dissipated between the points to the charge, power over charge, that cannot be PD. So this one is wrong. Our answer was this one here, which is C. The diagram shows 4 heaters and the current in each. Which heater has the greatest power dissipated? So we know that power is going to be I squared times R. So I'll just check with the calculator. For the first one, we have 8 squared times 2. That is 128. For the second one, we have 6 squared times 4. That is 144. The fourth one is 4 squared times 6. The third one, that is 96. And the last one is 2 squared times 8, which is 32. So the question is which heater has the greatest power? And you notice that the one with the greatest power is B. When a potential difference V is applied between the ends of a wire of diameter D and length L, the current in the wire is I. What is the current when the potential difference of 2 volts is applied between the ends of the wire of the same material? That means the resistivity is the same, diameter is twice D and length 2L. So we know that current is equal to V over R, and we also know that resistance R is equal to 4 rho L divided by pi D squared, because our resistance is equal to resistance is rho L over cross-sectional area, but area is equal to pi R squared, which is the same as pi D squared over 4. That's how I come up with this expression here. So I'm going to combine these two expressions because I know that R is V over I. So I will say that V over I is equal to 4 rho L over pi D squared. So for the first equation, I'll have that I'm making I the subject. I cross multiply, so it means I is going to be V times pi D squared divided by 4 rho L. That is going to be for the first wire. For the second wire, let its current be I2. I2 be its potential difference is twice V. Where there is V, I'm putting twice V times pi. Where there is diameter, I'll put there twice D, but it is squared. Divided by 4. The resistivity is the same, and the length is twice L. So here I'll put here 2L. I'll try to simplify this. When I square here, it becomes 4D squared. The 4 comes out, so it becomes 8 times V pi D squared divided by, when I pull out the 2, it will be twice times 4 rho L. Why have I done this? It's because I know that this ratio here is I. So this gives me 8 over 2, which is 4 times I. So the answer is going to be C, which is 4I. The diagram shows a junction in a circuit where 3 wires P, Q, and R meet. The currents in P and Q are 1 ampere and 3 amperes respectively in the directions shown. How many coulombs of charge pass a given point in the wire R in 5 seconds? Let me randomly choose the current here to be I. So the current there, which is I, according to Kirchhoff's first law, I plus 1 should equal 3. According to Kirchhoff's first law, the sum of currents entering the junction should equal the sum of currents leaving the junction. So that means I is going to be equal to 3 minus 1, which is 2 amperes. So we wanted the number of charges. So we know that charge is equal to IT. How many columns of charge? Charge is IT. So I is 2 times time, which is 5. And this gives us 10 columns. So our answer here is going to be D. The resistance of a thermistor decreases significantly as the temperature increases. The thermistor is kept in air. The air is at room temperature. Which graph best describes the way in which the current I in the thermistor depends upon the potential difference? So we know that current is equal to V over R. And it means if we have a graph of I against V, it means the gradient is equal to 1 over R. For a thermistor, they have said the resistance decreases. So resistance decreases, meaning the gradient must increase. So here, the gradient is increasing. The gradient must increase. So the resistance decreases. They say the resistance decreases. So it means more. This one is automatically wrong because here, if as V increases, it means the current is decreasing. Here it means the resistance is increasing. Then B, the resistance decreases and the gradient is also increasing. Okay. Then we have C. Then D is showing that the resistance, as the resistance decreases, the gradient also decreases. So we have to choose between B and C. What makes B automatically wrong is the fact that there is a current when there is no potential difference in a thermistor. So this one is automatically wrong. So our answer is going to be C. There is no current when there is no potential difference in a thermistor. When there is no PD across the thermistor, then there will be no current. But then you see the gradient is increasing. That means the resistance is decreasing. So the answer is going to be C. The diagram shows a potential divider circuit designed to provide a variable output PD, which gives the available range of output. So output is measured across this this 5 kilo ohm resistor. Let's say the maximum. The maximum output here is going to be, I'll call it V maximum, is going to be 5 kilo ohms divided by total resistance, which is 10 kilo ohms. The kilo cancels out. Then times 9, and I think this is 4.5. Half of 9 is 4.5. So the maximum should be 4.5. So this one and this one are wrong. This one is also automatically wrong. The maximum should be 4.5. So the answer is going to be B. Without even hesitation, the minimum cannot be 4.5 because the variable resistor can go to 0, which makes the PD across it 0. So the answer is B. In the circuit shown, the ammeters have negligible resistance and the voltmeters have infinite resistance. That means no current goes through the voltmeters. The readings on the meters are I1, I2, V1, and V2 as labeled on the diagram. Which is correct? I1 greater than I2. Let's check that one. This is 3 ohms. This is 6 ohms. If the current here is I1, it means the current here should be half because the current divides in the ratio of the resistances. So this one will be a half I1. This is 2 ohms. This is 2 ohms. If the current here is I2, the current here is also going to be I2. Using Kirchhoff's first law, the I1 will enter this junction. A half I1 also enters. So I1 plus a half I1, they are entered in that junction. Then this will be the one who's giving us I2 and I2 down. So this should be equal to twice I2. Or it is I2 plus I2. So this gives us 3 over 2. 3 over 2 I1 is equal to 2 I2, which means I1 is 4 over 3 I2. So it means I1 is greater than I2. I1 should be greater than I2, so C and D are wrong. Then let's check the readings of the voltmeters. The PD across V1, V1 is going to be I1 times 3, which is 3 times I1. Or it can be a half I1 times 6. And V2 is going to be equal to I2 times 2 ohms, which is twice I2. But remember, if I go back to the first equation here, V1 is going to be 3 times I1, which I1 is 4 over 3 I2. So V1 is 4, 3 times 4 over 3 I2, which gives us 4 I2. So it means V2 in terms of I2 is 2 I2 and V1 is 4 I2. So you see that V1 is twice V2. So V1 is greater than V2. V1 is greater than V2. So V1 should be greater than V2. So our answer is going to be A. The tensile strain may be measured by the change in electrical resistance of a strain gauge. A strain gauge consists of a folded metal wire, folded fine metal wire mounted on a flexible insulating backing sheet. The strain gauge is firmly attached to the specimen so that the strain in the metal wire is always identical to that in the specimen. When the strain in the specimen is increased, what happens to the resistance of the wire? So of course, when the strain in the specimen is increased, means length increases, cross-sectional area decreases. Resistance of a wire is equal to rho L over cross-section area. When length increases and cross-section area decreases, it means resistance increases. So it decreases, it actually increases. It increases because the length decreases. No, the length increases. It increases because the length increases and the cross-sectional area decreases. So the answer is going to be D. An electrical component has the following circuit symbol. Of course, this one is a fuse. So the answer is B. What does this symbol represent? That is a fuse. A variable resistor, we represent it like that. Light-dependent resistor, we represent it like this. You have already seen that. A thermistor, we represent it like this. We have already seen that. Three resistors are connected in series with a battery as shown in the diagram. The battery has negligible internal resistance. What is the potential difference across the 180 ohm resistor? So first of all, let's find the current. Current is equal to e.m.f, which is 6 divided by total resistance, which is 120 plus 150 plus 180. 120 plus 150 plus 180, which is 450. Then the PD across 180 ohms is going to be the current times the resistance. So that will be 6 over 450 times the resistance, which is 180. So 6 divided by 450 times 180, that gives us 2.4. So this is 2.4 volts. So our answer is going to be B. In the circuit below, the reading VT on the voltmeter changes from high to low. So VT changes from high to low as the temperature of the thermistor changes. The reading VL on the voltmeter changes from high to low as the level of light on the light-dependent resistor changes. The readings on VT and VL are both high. If this one is high, it means the resistance here is also high. And if the resistance is high, remember VT is the thermistor, it means here the temperature must be low. If this one is also, the VT is measured across the fixed resistor, so we shall change this analysis here. If VT is high, it means the PD here is high, but remember this is a fixed resistor. If the PD here, if V here is high, then V here should be low. V there should be low if V here is high. If V here is low, then it is because the resistance here is low. The resistance here is low. And if the resistance is low, it is because the temperature is high for a thermistor. So temperature should be high for a thermistor so that the resistance is low, so that the PD across the thermistor is low. So it means we choose from low. No, temperature should be high, so it means low is out. The temperature is high, so low is out. So we are going to choose from high, C and D. So we cross out A and B. Here V is measured across the variable resistance or the LDR. and they are saying VL is also high. So if VL is high, it means the resistance of the LDR is high, which means the light intensity is going to be low because they are inversely proportional. So the light intensity is going to be low. If the VL is to be high, the light intensity should be low. So the answer is going to be high and low. So the answer is going to be C. 4-point charges. 4-point charges, each of charge Q are placed on the edge of an insulating disk of radius R. The frequency of rotation of the disk is F. What is the equivalent electric current at the edge of the disk? So these charges are in series. So total charge is going to be 4 times Q. That is, they are in series. They are just joined. So total charge is going to be 4Q. What is the equivalent current? Current is equal to charge over time. So total charge is going to be 4Q divided by T. So current is equal to 4Q times 1 over T. And we know that frequency is going to be 1 over T. So it means current is going to be 4Q times F. So the answer is going to be A. An electrical component has a potential difference V across it and a current I through it. A graph of I against V is drawn and is marked in 3 sections, Wx, Xy, and Yz. In which ways does the resistance of component vary within each of the 3 sections? Okay, so we know that current is equal to V over R, which means the gradient of the graph of I against V is going to be 1 over R. So here, Wx, the gradient is constant, the resistance is constant. So Wx, in which way does the resistance of the component vary? Wx resistance is constant, so Wx is constant, so we eliminate increases. C and D are out. Then xy, you notice that the resistance, the gradient here is increasing. Here, gradient increases, so it means the resistance here decreases because when the gradient increases, the resistance decreases. They are inversely proportional. So gradient increases, resistance decreases. So xy, resistance decreases, so it decreases. Then yz, the gradient is decreasing. Here gradient decreases, which means resistance increases. So yz resistance increases. Here we say the gradient was constant. So our answer is going to be A. The diagram shows a potentiometer and a fixed resistor connected across a 12 volts battery of negligible internal resistance. The fixed resistor and the potentiometer each have resistance 20 ohms. The circuit is designed to provide a variable output voltage. What is the range of output voltage? Since the output is measured across here, it means when the contact is here, the output will be 0. And when the contact is here, the output will be, we use the potential divider formula. V out is going to be the resistance there, which is 20, over total resistance there, which is 40, times 12, which gives us 6 volts. So it means the maximum should be 6. So our answer is going to be A, 0 to 6. The resistance of a device is designed to change with the temperature. What is the device? That is a thermistor. A thermistor is the only device whose resistance changes with the temperature. LDR, that is light intensity, potential divider no, semiconductor diode no, so the answer is a thermistor. The diagram represents a circuit. Some currents have been shown on the diagram. What are the currents I1 and I2? So I1 is the total current entering this point here, and according to Kirchhoff's first law, I2 is going to be 20.2 plus 10.6, which gives us 30.8. So I2 is 30.8. So we eliminate A and C. Then I1 enters this junction, 10.6 enters that junction, 10.8 leaves. So again, Kirchhoff's first law. I1 plus 10.6 should give us 10.8. So it means I1 is equal to 10.8 minus 10.6, which is 0.2 milliamperes. So our answer here is going to be 0.2 I1, 30.8 I2. So the answer is going to be B. Which circuit has a resistance of 40 ohms between the terminals? Let's inspect these circuits. So these ones are for in parallel. When if you're an expert by now, you don't waste much time finding total resistance of these ones in parallel. An expert will be able to see that if these four are in parallel, their total resistance is going to be 4 times 1 over 100, which is 4 over 100. Then you get the reciprocal, that gives you 50. So these ones here, not 50, 25, these ones here are giving us a resistor which is of 25 ohms, just one, which will be in series with 100. That means total resistance here is going to be equal to 125 ohms. If that is hard for you to see, you can again do this. 1 over resistance in parallel is going to be 1 over 100 plus 1 over 100 plus 1 over 100 plus 1 over 100. That is 4 times, meaning 1 over resistance in parallel is equal to 4 into 1 over 100. Then you get the reciprocal. So when I get the reciprocal, resistance in parallel is going to be 100 divided by 4, which gives us 25 ohms. So these 4 give us 25, but the 25 will be in series with 100. Resistance in series we just add. So total resistance is 125 there. Then this one, B is 100 and 100 are in parallel. Then these ones are in series, they give us 200 here. So again, I will say 1 over resistance in parallel is going to be equal to 1 over 100 plus 1 over 100 plus 1 over 200. So the 1 over resistance in parallel is going to be the LCM, which is 200. So 200 by 1, this is 1, this is 2 plus 2 plus 200 by 200 is 1, so that is plus 1. So that is plus 1. So then I get the reciprocal. Resistance in parallel will be 200 divided by 5, which I think is 40 ohms. So the answer is automatically B. Which electrical quantity would be result of calculation in which energy is divided by charge? That is either EMF or potential difference. So the answer is going to be B. Two heating coils X and Y of resistance Rx and Ry respectively deliver the same power when 12 volts is applied across X and 6 volts is applied across Y. What is the ratio Rx over Ry? Okay, so we know that power is equal to V squared divided by R. Remember, the power is going to be the same. So I'll say for X, the power in X is going to be the V across X, which is 12 squared divided by the resistance of X. Let me call it Rx. This should be the same as the power across Y, whose V is 6 squared divided by Ry. Remember, I want Rx over Ry. So I'll take Rx to the right hand side and bring 6 squared down here. So we shall have that 12 squared divided by 6 squared is equal to Rx over Ry. So from the calculator, 12 squared divided by 6 squared, that gives us 4. So the ratio is going to be 4. So our answer is going to be D. So Rx over Ry is equal to 4. The answer is D. A battery of negligible internal resistance is connected to 10 ohm resistors in series. So these are 10 ohm resistors in series. What charge flows through each of the 10 ohm resistors in 1 minute? So we know charge is going to be current times time. All we need is the current here. And the current is going to be the EMF, which is 6, divided by total resistance, which is 20. So it means the charge is going to be 6 over 20 times the time, which time is 60 seconds, because it should be in seconds. 1 minute is 60 seconds. So you have 6 times 60 divided by 20, which gives us 18. So the charge here is 18 coulombs. So the answer is going to be D. Two wires P and Q have resistances Rp and Rq respectively. Wire P is twice as long as wire Q and has twice diameter of wire Q. The wires are made of the same material. What is the ratio? Rp over Rq. So we have noticed that resistance is equal to rho L over cross-sectional area. They gave us the mentioned diameter. So we shall bring in the diameter. So resistance will be 4 rho L over diameter over cross-sectional area. Okay, area is pi d squared over 4, so the 4 goes up. So in the denominator we have pi times d squared. So we are going to come up, they said the wires P and Q have the same resistance, have resistances Rp and Rq respectively. The wires are made of the same material, so they have the same resistivity. So let me first write an expression for resistance of wire Q. Resistance of wire Q will be equal to 4 rho L over pi d squared, because they told us wire P is twice as long as wire Q. So let the length of wire Q be L. Then wire P again has twice the diameter of wire Q. So let the diameter of wire Q be D. Then resistance of wire P is going to be 4. They are from the same material, so resistivity is the same. The length of wire P is twice, so this will be twice L divided by pi. The diameter is also twice, so this is twice D, but it is squared. So when I factor out, I have twice into 4 rho L divided by, when I square 2 pi d, I get 4d squared, so I pull out 4 and I remain with the pi d squared. You will notice that this quantity here is the same as that for Rq. So it means Rp is equal to 2 over 1 over 4, that is a half Rq. So I want the ratio Rp over Rq. So it means Rp divided by Rq is equal to a half, which is 0.5. So the answer is going to be A. A potential divider consists of a fixed resistor R and light-dependent resistor LDR. What happens to the voltmeter reading, and why does it happen when the light intensity on the LDR increases? So when light intensity increases, remember the LDR is a negative coefficient device. When the light intensity increases, it means the resistance of the LDR must decrease, which means because PD is equal to I times R, since the resistance has decreased, the PD of the LDR must decrease. So the question is, what happens to the voltmeter reading? So the voltmeter reading decreases. So we eliminate increases. The voltmeter reading decreases. And why does it decrease? It is because the resistance of the LDR decreases. So the answer is going to be A. The circuit is designed to trigger an alarm system when the input voltage exceeds some present value. It does this by comparing Vout with a fixed reference voltage, which is set at 4.8 volts. So this is kilo ohms. Okay, Vout is equal to 4.8. What is the input voltage Vin? So if Vout is 4.8, we know that Vout is equal to resistance there, where the Vout is measured over total resistance in that branch, then times Vin, that is the potential divider formula. So if V out is 4.8, then this should be called the resistance there, which is 10 kilo ohms, over total resistance there, which is 10 plus 15, which is 25 kilo ohms, then times the V in, which we want to find. So kilo ohms has cancelled. So V in is going to be 4.8 times 25 divided by 10, which is 12. So V in is going to be 12 volts. So 12 volts is D. A potentiometer is used as shown to compare the EMFs of two cells. The balance points for cells X, Y, and Y are 0.7 and 0.9 respectively. If the EMF of cell X is 1.1, remember EMF of X is going to be equal to PD across the balance length. PD across the balance length. PD across the balance length. So it means, and PD across the balance length is going to be equal to a constant times the length, the balance length, which I'm calling Lx. So the EMF across of cell X is 1.1. This should be equal to a constant times the length X, which is 0.7. Then what is the EMF of cell Y? So the EMF of cell Y is also going to be the PD across the balance length for Y, which is the PD across, which is going to be the constant K times the balance length Y. So it will be equal to the constant K times the balance length of Y. So this is going to be the constant K. The balance length of Y is 0.9. So we just divide the two equations. EMF of Y divided by 1.1 is going to be K times 0.9 divided by K times 0.7. So K has cancelled out. So it means EMF of Y will be 0.9 divided by 0.7, then times 1.1, which gives us 1.4. So EMF of cell Y is going to be 1.4 volts. So the answer is going to be D. When four identical resistors are connected, as shown in the diagram 1, the ammeter reads 1 ampere and the voltmeter reads 0. So if the ammeter reads 1 ampere, remember these are identical. So this is going to be 1 ampere, this is also 1 ampere. That means total current in this circuit here is going to be 2 amperes. So total current from the battery is 2 amperes. Then the resistors and meters, of course, the PD across each is the same. This is 3 volts, 3 volts because they are identical, and the current through them is the same. So that is 3 volts. The voltmeter is going to automatically read 0. The resistors and meters are reconnected to the supply as shown in the diagram 2. What are the meter readings in the diagram 2? So the current which is coming from the battery here is going to still be 2 amperes. Now it is going to divide at this junction. 1 ampere takes this route, another 1 ampere takes the other route. So again, the reading of the ammeter is going to be 1 ampere. So we cancel out these ones here. Why is it 1 ampere? Because again, you see that the current will go through these two resistors because the voltmeter has high resistance. The current divides at this point, takes this route. There are two resistors this side, and there are two resistors the other side as it was before. So it means the current in the reading of the ammeter is still going to be 1 ampere. The 2 amperes from the battery divides equally since the resistors are identical. So 1 ampere, 1 ampere. But then, because the resistors are identical, this is resistance R, it means at this junction here, the potential at this junction here is going to be the same potential at this junction here because the resistors, remember, are identical. Resistors are identical. The current through them is the same. So the potential at this junction is going to be the same as the potential at this point here. Therefore, the potential difference is going to be 0 because we subtract the difference in the potentials. But if the potentials are the same, then the potential difference is going to be 0. Therefore, the answer is going to be A. The potential here is going to be the 1 ampere times R. The potential here, the potential will also be 1 ampere times R. That means the potential difference is 1 R minus 1R, which will be 0. So the answer is going to be A. Two wires P and Q are made of the same material. That means they have the same resistivity and of the same length L, are connected in parallel. So that means the PD across them is the same. Wire P has diameter 2 millimeters and wire Q has diameter 1 millimeter. What is the ratio current in P over current in Q? So this is just a question we have already answered. So very first, we know that our resistance is equal to rho L over cross-section area. They have mentioned the diameter, so resistance will be 4 rho L over pi d squared. Remember the PD is the same, and also remember that resistance, that PD is equal to I times R. So I'm just going to get two equations for the PD. Because the PD is the same, I will just equate. So PdV is equal to, for the first wire P, the current is I in P, resistance in P. P and Q are made of the same material, so the resistance will be times 4. Same material, resistivity is rho. Same length is L over pi. Diameter of P, I'm looking at P. Wire P has diameter of 2. I will not change the units of diameter, so I'll just say 2 squared. The same PD should be obtained for Q, so I'll just say equals to the current in Q, which is IQ. This is 4, same resistivity, same length, over pi. The diameter of Q is 1 squared, 1 millimeter. I've not changed the units because I'm dividing, they are cancelling out. So using a different color, you see that 4 has cancelled and pi has cancelled. So IP over IQ, IP divided by, or IP over 2 squared, which is 4, is equal to IQ over 1 squared, which is 1. So it means IP divided by IQ is going to be equal to 4 over 1, which makes our answer to be precisely D. The charge that a fully charged 12-volt car battery can supply is 100 kilocoulombs. The starter motor of the car requires 200 amperes for an average period of 2 seconds. The battery does not recharge because of a fault. What is the maximum number of times the starter motor of the car can be used? Okay, let's first find the charge for one time. If it is used for one time, charge is going to be current times time, which is going to be 200 times 2, which is giving us 400 coulombs. But the battery can supply 100 coulombs. So it means the number of times is going to be 100,000. That is 100 kilocoulombs divided by 400, which gives us 100,000 divided by 400, which is 250. So the battery will be used 250 times and before it runs out. The diagram shows a circuit containing 3 resistors in parallel. The battery has e.m.f 12 and negative internal resistance. So the ammeter reading is 3.2. So the current here is 3.2 amperes. That is total current. But we know that total current is equal to the e.m.f over total resistance. So we can find total resistance. So total resistance is going to be equal to e.m.f, which is 12, over total current, which is 3.2. 12 divided by 3.2, that gives us, okay, I'll write it as a fraction. This gives us 15 over 4 ohms. That's total resistance. Then these resistors are in series, are in parallel. Then we get the reciprocals. So 1 over total resistance is going to be equal to 1 over 10 plus 1 over 10 plus 1 over x. So 1 over total resistance is going to be the reciprocal of 15 over 4, which becomes 4 over 15 is equal to 1 over 10 plus 1 over 10 is 2 over 10 plus 1 over x. So 1 over x will be equal to 4 over 15 minus 2 over 10. 4 over 15 minus 2 over 10, 4 divided by 15 minus 2 divided by 10. So this is giving us 1 over 15. That's 1 over x is 1 over 15, which implies that x is equal to 15 ohms. So our answer is going to be D. The EMF of a battery is 9 volts. The reading on the high resistance voltmeter is 7.5. So the PD across here is 7.5. The terminal PD. What is the current? So current is going to be the terminal PD divided by the resistance, which will be 7.5 divided by 15. 7.5 divided by 15, that is a half, which is 0.5. So this is 0.5 amperes. So the answer is going to be B. The diagram shows a potentiometer circuit. The contact T is placed on the wire and moved along the wire until the galvanometer reading is 0. The length xt is then noted. Okay. In order to calculate the potential difference per unit length, that is PD per centimeter, on the wire X, which value must also be known. Remember, the cell EMF E2 is going to be equal to the PD across XT, which PD across XT is equal to a constant, which is the PD per centimeter, or PD per unit length, then times length XT. So in order to find the PD per centimeter, if E2 is known, then we also need length. They said length xt is noted. So length xt is noted. We want to find PD per centimeter. So E2 must also be known. So the EMF of the cell E2 must be known, because the PD per centimeter will be equal to the EMF E2 over the length xt. So the answer is going to be B. A cell is connected to a resistor. At any given moment, the potential difference across the cell is less than EMF. That is very true. EMF is equal to the PD, the terminal PD plus the lost volts. That means the terminal PD is going to be the EMF minus the lost volts, which is current times resistance. So that means some energy is dissipated within the internal resistance of the cell if the terminal PD or the PD across the cell is less than the EMF. Which statement explains this? The cell is continuously discharging, that's not true. The connecting wires has some resistance, that one does not account for that. The energy is needed to drive the charge through the cell. I think that is true because there is some internal resistance. Energy is needed to drive the charge through the cell because there is some internal resistance. That energy is the lost volts. So the answer is going to be C. A cylindrical wire 4 meters long has a resistance 31 ohms and is made of a metal of resistivity 1.0 times 10 power negative 6 ohm meters. What is the radius of cross section of the wire? So we know the resistance is equal to rho L over cross sectional area, which is rho L. Since they are talking about radius, this will be over pi r squared. So you notice that r will be the square root of this will be rho L over pi times capital R. So this will be the square root of rho is 1.0 times 10 power negative 6. The length is 4 meters over pi times the resistance, which is 31. So 1 exponent negative 6 times 4 divided by pi times 31. Then I find the square root. So I'm getting 2.0 times 10 power negative 4. 2.0 times 10 power negative 4 in meters. So that is the radius, which means the answer is going to be D. Each of Kirchhoff's two laws presumes that some quantity is conserved. Remember, first law is charge, second law is energy. Which law states Kirchhoff's first and names the quantity that is conserved? The algebraic sum of currents into a junction is 0, and that is charge. The answer is A. The algebraic sum of current into junction is 0. This is not conservation of energy. The EMF in a loop is equal to the algebraic sum of the product of current and resistance around the loop. And this one is showing conservation of charge, which is wrong. EMF cannot talk about charge when you're referring to EMF. The EMF in a loop is equal to the algebraic sum of the product of current and resistance around the loop. That's conservation of energy. Of course, this would be making some sense, but the algebraic sum of EMF and potential drops is going to be equal to 0. The algebraic sum of EMFs and the potential drops is equal to 0. So the answer is going to be A. The diagram shows the symbol for a wire carrying a current I. What does this current represent? Of course, current is the rate of flow of charge carriers. So what does this current represent? The amount of charge flowing past a point per second. So the answer is going to be A. The number of electrons flowing past a point xy per second. The number of positive ions flowing past a point per second. The number of protons. So the answer is charge flowing past a point per second. So the answer is A. A potential divider circuit consists of resistors of resistance R1 and R2 connected to an input potential difference V0 and gives an output of V. So the output is V. What is the value of V? So we just look for the potential divider formula. V is going to be the resistance across that point, which is R1, over total resistance, which is R1 plus R2, times the voltage supply, which is V0. So the answer here is going to be B. And this marks the end of electricity and DC circuits. I hope you learned something from electricity and DC circuits. Of course, after recording paper 2 of February, March 2023, next will be the formation of solids. Thank you for watching these videos and thank you for learning with me. I wish you all the best. Bye bye.